Hi guys, my name is Kyle Demanis, and today we're going to talk about biomechanics. Biomechanics is a study of how mechanical laws relate to movement and structure of the human body. And at Georgia Tech in the BME 3400 class, the class is generally divided into three components. So statics, where there's no movement happening on the body, so we can say the sum of the forces is equal to 0. Dynamics, where there is motion happening, and we can say the sum of the forces is equal to mass times acceleration. And then finally mechanics, where that relates more to statics, but just seeing how all these laws are integrated into the human body. And so within mechanics, we generally focus on three types of loading. So we can focus on axial loading, so the horizontal forces that can act on, for example, your arm. Then you have torsional loading, so what twisting forces act on the human body. And then finally bending. So these are the vertical forces that act on different parts of the body. And today we're going to focus on bending. So let's get started. So bending is the stress and strain that happens from a load perpendicular to the long axis. So the goal that we're trying to achieve with bending is to find the internal forces happening on an object, the stress, the strain, and the deformation. So the first thing we're going to look at are the internal forces. So there are two main internal forces that we're going to look at. So one is shear force. Shear force is the force acting on an object in a perpendicular direction at the cross-sectional area to the extension of an object. So this is similar to when you're looking at a wing, the air going over the side of the wing is the shear force. And this can be denoted as V. Then the second internal force that we're looking at is the moment force, or the bending moment. This is the sum of the moments of the forces at the cross-sectional area and can be denoted as M. And we can go ahead and relate these two as V is the derivative of the moment in terms of some position. So this is something that we can use as a relationship later on when we do an example problem. But now we're going to go ahead and talk about how to actually solve for these forces and create diagrams along the length of a beam. So before we get into a quick example, there's some assumptions that we have to make. Because the human body is very complex, we have to assume that whatever object we're looking at is elastic, meaning that it returns to its original shape after being deformed. It's isotropic, meaning that it maintains the same physical properties in all directions. And finally, it is linear, meaning that it obeys Hooke's law and Young's modulus is constant over a varied range of strains. 2, we're assuming that the total length change in the x direction is very minimal or almost we can disregard it. And then finally, 3, the cross-sectional area shape can remain uniform throughout the entire object. So looking at an example of a beam with a pin joint and roller joint and a force P at 2L/3, we can go ahead and solve for our internal forces. So our first step is to solve for our whole free body diagram. So we can replace our pin joint with an X and Y force at A and our roller joint with a force at point B. So that we can go ahead and use the sum of the forces in the X direction to solve for FAX. And when we set it equal to 0, we can see that FAX is equal to 0. And then when we go ahead and solve for the sum of the moments at point A, we can assume that counterclockwise is the positive direction. We can go ahead and see that FAB is equal to 2P/3. And when we go ahead and solve for the sum of the forces in the y direction, we can solve that FAY is equal to P/3. Now our second step is to go ahead and make our cuts. So we're going to look at our cut free body diagram so that we can go ahead and find the values of the internal forces. But one major thing to keep in mind is that we should never make a cut at a change or a discontinuity. So we cannot make any cuts at 2/3 where that P force is acting. So we go ahead and make a cut one before that, so between 0 and 2L/3, and one after, so between 2L/3 and L. So now that we made our cuts, we can go ahead and solve for our internal forces, so our shear force V and our moment force M. So when we look at our first cut from 0 to X to 2L/3, we can go ahead and see that we've revealed those internal V and M forces. So as if we put those two pieces back together, they would form one beam. So we can look at either the left piece or the right piece and still solve for the same value. So I'll go ahead and take the left piece, but when we go ahead and solve for the sum of the forces in the x direction, we can see that FAX is going to be equal to 0. And if we do the sum of the forces in the y, we'll see that V is equal to P/3. And then when we do the sum of the moments about A, assuming that the length of that piece of the beam is some arbitrary value x, we can see that the moment force is equal to Px/3 from 0 to x to 2L/3. Now similarly, if we look at our second cut from 2L/3 to L, we can do the same exact thing. You can see that you can either tackle the left piece or the right piece. You'll get the same exact value. So we're going to go ahead and look at the left piece. So do the same exact thing that you do the sum of the forces in the x direction, and we see that FAX is equal to 0. And when you do the sum of the forces in the y direction, we can see that V1 is equal to negative 2p/3. And when you do the sum of the moments about point A, you can see that M1 is equal to positive 2pl over 3 minus 2px over 3. So now we have the values for our shear force and our moment force at these two different cuts. So now that we've solved for our values of shear and moment force at these two different cuts, we can go ahead and create our shear and moment diagrams based on position X. So when we're looking at our shear force, we can see that from 0 to 2L over 3, it's at a constant P over 3. So we can go ahead and graph it as such. And then from 2L over 3 to L, it's at a constant negative 2P over 3 at that point. So we can draw that as such as well. And when we're looking at our moment diagram, we see that at our first cut, M is equal to Px over 3. So we can go ahead and graph it and see that at 2L over 3, M is equal to 2PL over 9. And when we go ahead and solve for the latter part for our second cut, we can see that the moment is 2PL over 3 minus 2PX over 3. And you can actually see if you plug in for x equals 2L over 3, for both of these equations, they'll equate to the same value of 2PL over 9. So why are these important? So now that we've found our internal forces, this will allow us to solve for other variables. So one, we can find our normal stress. So sigma equals negative mxy over ix. So what this allows us to see is what critical stresses and how much can an object hold until it breaks. So this is important to see how much force your body can handle or different objects. And another thing you can find is your shear stress. So that's denoted by tau equals VQ over IT. And similarly, this can be used to understand different properties of the human body or different objects. And then finally, we can find deflection or some kind of deformation, which is the distance that a point on a beam changes due to an applied load denoted as nu. And so what we can actually do is qualitatively see how much, due to this force P at 2L over 3, that this beam deforms over time or over position. And that was a short look into bending in biomechanics, so I hope you enjoyed the video and learned a lot, and feel free to reach out to me if you have any further questions. Thank you!